Simple things first. In the 16th century, Galileo observed a swinging lamp and measured its oscillation period by taking his own pulse. How can we describe a swinging pendulum? The tip of the pendulum moves on the blue circle. Let's place this circle on the cylinder, like so. Every point of the circle represents a position of the pendulum. The red point, for example, is the position at the bottom. Its speed, given by the red vector, is described by a number. The number is positive if it rotates in one direction, and negative if it rotates in the other. We can represent this number in the cylinder's vertical position. So, a single point on the cylinder describes both the position and the speed. The first coordinate, on the circle, tells us where the swing is, and the second, vertical coordinate, tells us how fast it is swinging. So now, let's put gravity to work and watch the swing. For now, we will assume there is no friction at all. The swinging will never end. If the initial position is low, and the initial velocity is not too large, then the pendulum moves periodically. We all know that. If we launch it faster, perhaps too fast, it will go all the way around. It is still a periodic movement, but not in the same way. Look at the trajectory on the cylinder. It follows a vector field. Now observe the more realistic situation, where there is friction. The oscillation slowly decreases, and then finally the pendulum slows to a stop. Remember Aristotle's theory. The swing is now back in its natural position at the bottom. Observe the corresponding vector field on the cylinder. Trajectories eventually spiral into the resting position. This equilibrium position is called a stable attractor. A swing with friction is not very much fun because it eventually stops. So we have to give the swing a push to make it go really high. This is also the point of view of the gentleman represented by the painter Fragonard. He seems very interested in the swing. Let's imagine that the pendulum, in addition to gravity and friction, is also subjected to a pushing force coming from a small nozzle. This is a very modern pendulum. It comes with a jet engine. For example, suppose the nozzle activates only when the speed and the height of the pendulum are lower than a certain value. If we start too slowly, we are pushed, and we accelerate and accelerate until the pushing stops because the pendulum is going too fast. Friction takes over, and it slows down and slows down until the push comes to the rescue again, and so on. the motion finally stabilizes on a periodic regime. Poincaré calls this a limit cycle. This is the opposite of chaos, in a way, the periodic regime. Everything is in sync. Here is what is called the phase portrait of the cylinder. The limit cycle is in red. We see a spiraling trajectory that gradually becomes the periodic trajectory. Here is a simple example that illustrates all of this in ecology. The Lotka-Volterra model, dating from the 1930s. Two populations share a territory. For example, rabbits and foxes. We will instead imagine a pond with ducks and water lilies. See the ducks eating the water lilies. When there are only a few ducks, then they eat only a few lilies. The water lily population, therefore, grows rapidly. When there are a few ducks and many water lilies, the ducks are well fed and their number increases. But a lot of ducks eat a lot of water lilies. When there are fewer and fewer water lilies, the ducks have less and less to eat, and their number decreases. So we have come full circle and can start again. We can record the situation at any given moment in time using a point on a plane. The first coordinate represents the number of water lilies, and the second represents the number of ducks. In fact, we get a vector field in the plane. Over time, the ducks and lilies follow a trajectory of the vector field and reach a limit cycle. The populations of ducks and water lilies eventually oscillate periodically. The belief that any motion, perhaps after a short transition period, eventually stabilizes, either by stopping or by oscillating periodically, has dominated science for a very long time. One of the first theorems in the theory of dynamical systems, by Poincaré in the late 19th century, seemed to justify this. It is about vector fields in the plane. Imagine a vector field that looks like this. In fact, we don't know the vector field everywhere, but we know how it behaves close to this circle. Take a trajectory that enters the disk. Where can it go? Well, the Poincaré-Bendixson theorem says there are two possible cases. The trajectory will either get very close to an equilibrium position, as we see here. This is what we saw for the damped pendulum. Or it must approach a limit cycle. How do we prove such a theorem? Here is the main idea. Take a point on the circle and observe the trajectory through the point entering the circle. Stop. Let's stop at a point P. Look at all of the trajectories in the vicinity of P. Is it possible that the trajectory continues and returns to the vicinity of P? Let's suppose that it indeed returns to a nearby point, Q. The arc of the trajectory between P and Q, followed by the line QP, forms a closed curve. This is the boundary of a certain area, drawn in blue. We can see that a trajectory that starts from Q enters the blue area, and then it can't get out anymore. It's trapped. In order to exit, it should cross the arc PQ. However, two trajectories cannot cross. Why not? Well, if two trajectories pass through the same point, this would contradict the Cauchy-Lipschitz theorem. There is only a single trajectory through any given point. The trajectory starting from Q cannot escape through the line QP either. There, the vector field is coming in, not going out. You can see that the trajectory from P may well return very close to P, but then it is condemned to never escape. We say, in this situation, that there is no recurrence. This is the main idea of the Poincare-Bendixson theorem. This theorem marks the beginning of what is now called the qualitative theory of dynamical systems. Even if we have only an imperfect knowledge of a vector field, we can often understand the behavior of its trajectories. In the case of the plane, everything goes well. The trajectories eventually become periodic, or they approach a point of equilibrium. But Poincare soon discovered that his theorem is valid only for vector fields in 2 dimensions. That is to say, for very small systems. For 3 dimensions and higher, we will see that the situation can be much more complicated and very beautiful. No more nice simple limit cycles. Welcome to the world of chaos.